Good morning, children. As in the two classes, we have started thermochemistry. Let us continue thermochemistry. Okay, some of the children, yesterday I have given one assignment as 6.13. Some of the children have answered and they have posted the answer to me. Okay, I felt happy that they are showing good response. Remember one thing, whether they are going to conduct annual theory exam or not, we need to appear for competitive exam. Correct? And to appear for the competitive exam, whatever we are completing in the class, children, that you need to concentrate. That you need to, because first year theory exam is not your destination. Still you have to prepare for the second PUC still, because many of the topic of the first year and second year are in continuation. As we are taking the topic thermochemistry, this topic, it will help you even in the second year topics. Because when you'll go for the second year, as in the competitive exam, you are having first year and second year 50-50%. That time we need all these concepts. That's why better that whatever the assignment will be given to you, you need to respond in a good way. Some of the children have answered very well. They have posted in the 5-10 minutes only, they have posted their solution. Really very good children, well done. Same thing, same this one tempo we need to maintain. Let us come to the topic. Let us continue the topic, thermochemistry. Okay, let us come to the topic, thermochemistry. Okay. Topic is very interesting. Okay, many of the things are there which are like with respect to their name itself we can identify. Thermochemistry. Let us continue topic, children. Thermochemistry. Have you remembered that in the previous class we have started types of enthalpies of reaction? What we have started, have you remembered? Types of enthalpies of reaction. Types of enthalpies of reaction. Types of enthalpies of reaction. In that we have completed 2 enthalpies of reaction. You may be remembering all those. First we have completed with respect to what, children? We have completed with respect to enthalpy of formation. Enthalpy of formation. Just I'll write the name because already we have completed this part. I need not to explain once again. And second also we have completed enthalpy of combustion. Enthalpy of combustion. Okay. Enthalpy of formation and the enthalpy of combustion, as we have completed the 2 subclasses in previous this one topic, that is enthalpy of formation, which is represented as delta HF. If it is a standard, that time we need to take the superscript as 0. Okay. Another point we said that enthalpy of combustion as delta HC. If it is a standard, we can take it as with respect to 0. Let us come to now the third one, that is enthalpy of solution. Let us come to third one, enthalpy of solution. Enthalpy of solution. Enthalpy of solution. We can write it as delta H solution. All these symbolical representation are which will help you lot to understand that what we want to define. Come to the point, that is, what do you mean by enthalpy of solution? We know very well that solution can be prepared by dissolving 1 mole of solute in excess of solvent. And usually solvent will use it as water. That's why we'll say that when 1 mole of a solute is added to excess of solvent, okay, the amount of heat accompanied during the preparation of solution, During the preparation of solution, whatever the amount of heat is accompanied, it is called as enthalpy of solution. It is called as what? Enthalpy of solution. Let us come to the point. Enthalpy of solution can be defined as the heat accompanied. Enthalpy of solution can be defined as the heat accompanied during addition of addition of 1 mole of solute, 1 mole of solute, that is substance, 1 mole of solute, that is substance, in excess of solvent, in excess of solvent. Let me repeat the sentence. Whenever we are defining with respect to the solution, we can say that amount of the heat accompanied. Look at over here the sentence. The heat accompanied during the addition of 1 mole of solute. Solute must be how much, children? 1 mole. That is 1 mole of the solute or the substance in excess of solvent. In excess of solvent. As I said earlier that usually we are using the solvent as water. Usually we are using the solvent as water. So we can say that whenever the heat is accompanied, heat may be absorbed, heat may be liberated. Therefore, the heat accompanied during the addition of 1 mole of a substance or the solute in excess of solvent in such a way that further dilution will not change enthalpy value, in such a way that this sentence is most important, in such a way that further dilution does not change enthalpy value, does not change delta H value. Enthalpy value is nothing but what? Delta H value. Repeat the sentence over here. The amount of heat accompanied. Amount of heat accompanied is nothing but what? Heat may be liberated, heat may be absorbed. Amount of heat accompanied during the addition of 1 mole of solute. Solute must be how much, children? 1 mole. Have you remembered that? Even in the formation, enthalpy of formation also, we have taken the solute as 1 mole. Even in the enthalpy of combustion also, we have taken the substance as 1 mole. Even in this also, we are going to take what, children? We are going to take 1 mole of the solute in excess of solvent in such a way that further dilution does not change enthalpy value. Further dilution should not change enthalpy value. It is called as enthalpy of solution. Let us move to the example one by one, children. If we are going to see the example, we can understand better over here. We can write example. Sodium chloride dissolved in excess of water. What we can say? When the sodium chloride is dissolved in excess of water, sodium chloride dissolved in excess of water. Remember one thing, whenever we are going to take water as excess, even we can write it as AQ. We can write it as AQ, that is sodium chloride aqueous solution. Solid sodium chloride dissolved in excess of water to produce aqueous sodium chloride solution, and the delta H value is, delta H solution is plus 5.35 kilojoule per mole. Plus 5.35 kilojoule per mole. So always you need to remember that this excess of water can also be written it as AQ. Excess of water can be written it as AQ. We have to dissolve 1 mole of a solute. We have to dissolve 1 mole of a solute in excess of solvent in such a way that further dilution does not change enthalpy value. Further dilution should not change enthalpy value. That point is called as enthalpy of solution. Enthalpy of solution. Here, in all the type of enthalpies, have you observed that we are going to correlate heat accompanied with the particular type of the reaction. If it is a formation of a substance from its elements. If it is a combustion, burning of a substance in presence of air or oxygen. If it is a solution, we are going to take 1 mole of a solute in excess of water or excess of solvent. If we are going to take the example like hydrochloric acid solution, if I am going to prepare, okay, in the purest form, like the fuming hydrochloric acid, HCl gas, if I am going to add with 25 moles of water, 25 moles of water, okay. 25 moles of water. 25 moles of water. We are going to prepare what, children? HCl with 25 moles of water as a aqueous. And remember one thing, whenever the hydrochloric acid is added with water, the enthalpy value is minus 72.3 kilojoule per mole. Minus 72.3 kilojoule per mole. Instead of taking 25 moles of water, if I am going to take 40 moles of water, what happened? Let us see one by one. And in all the cases, HCl must be 1 mole, because as per the standard definition, substance must be 1 mole only. That's why we are going to take with respect to what, children? HCl, 40 H2O, 40 H2O, and the delta H value will become it as minus 73.5 kilojoule per mole. It means that we are adding excess of water, enthalpy value are going to be changed. But the point will reach when hydrochloric acid treated with excess of water. Hydrochloric acid treated with excess of water. Water is excess. That time we are going to prepare hydrochloric acid aqueous solution, and the delta H will be minus 75 kilojoule per mole. Minus 75 kilojoule per mole. So this, instead of writing these two reaction, this reaction is more than enough to explain enthalpy of solution. That's why whenever they are asking the question, to write with the example. Always you need to remember that substance must be 1 mole and the solvent must be excess. When the solvent is excess, even we can write this as aqueous. That's why we can define, let me repeat the sentence, amount of heat accompanied when 1 mole of a solute is added to excess of solvent in such a way that further dilution will not change enthalpy value. It means that after adding excess of water, even if we are going to add the excess of water, enthalpy value will remain constant as minus 75 kilojoule per mole. And that point is called as enthalpy of solution. That point is called as what, children? Enthalpy of solution. This is about third type. Now let us move to fourth one. That is enthalpy of hydration. Okay. Let us move to the point, enthalpy of hydration. Enthalpy of hydration. Fourth one. Enthalpy of hydration. Enthalpy of hydration, delta H hydration. Name itself indicates that whenever the substance in the crude form, it will be anhydrous. Means that anhydrous salt are crude form, hydrated salt are in the crystalline form. And remember one thing, every mole of the solute will be accompanied with a specified amount of water. With specified amount of water. You cannot compare the barium chloride with copper sulfate. You cannot compare copper sulfate with other salt like ammonium chloride. So it means that every salt will be accompanied with specified amount of water. It is called as enthalpy of hydration. Therefore, enthalpy of hydration can be defined as the heat accompanied heat accompanied, when we are using the term accompanied, it may be negative, it may be positive, by converting or for converting 1 mole of the salt in anhydrous form. We can say that 1 mole of the salt or the 1 mole of anhydrous salt. 1 mole of anhydrous salt. 1 mole of anhydrous. Particularly, I have taken here different color because 1 mole of anhydrous salt will be gets converted into hydrated salt by taking the specified amount of water. Converted to water, hydrated salt. Hydrated salt with a specified amount of water. With specified amount of water. Remember one thing, there is a difference between enthalpy of solution and enthalpy of hydration. Enthalpy of solution said that when 1 mole of a solute is added to excess of solvent, 1 mole of a solute is added to excess of solvent in such a way that further dilution does not change enthalpy value. Further dilution should not change enthalpy value. Now, in case of the enthalpy of hydration, the enthalpy of hydration, as we said that enthalpy of hydration can be defined as enthalpy of hydration can be defined as the amount of heat accompanied by converting 1 mole of anhydrous salt. Means anhydrous salt are converted into hydrated salt. Anhydrous salt are converted into hydrated salt. That point is called as what, children? That is called as enthalpy of hydration. For example, copper sulfate in the solid state, anhydrous copper sulfate in the solid state with 5 moles of water. 5 moles of water. Okay, liquid form converted into crystalline form of copper sulfate. Crystalline form of copper sulfate. This is also in the solid state. This is also in the solid state. Then delta H hydration. Delta H hydration will be equal to minus 75.2 kilojoule per mole. Listen here once again the sentence. Copper sulfate has the capacity to combine with 5 moles of water. Copper sulfate has the capacity to combine with how many specified amount of water? 5 moles of water. 5 moles of water. Whereas if I am going to take instead of copper sulfate, barium chloride. Barium chloride solid has formed hydrated salt by taking 2 moles of water to get barium chloride with 2 moles of water in the crystalline form. In the crystalline form, and the enthalpy value will be equal to, that is enthalpy of hydration will be equal to minus 29.4 kilojoule per mole. This delta H value will be different from book to book. That's why that you need not to worry about that. You need to concentrate on sign. Are they exothermic or are they endothermic? Okay, so we can say that whenever we are dealing with enthalpy of hydration, we are converting anhydrous salt to hydrated salt. Remember one thing, anhydrous salt will be crude form. Anhydrous salt will be crude form, whereas the hydrated salt will be in the form of a perfectly crystalline solid. That's why the enthalpy of hydration can be defined as amount of heat accompanied to convert anhydrous salt. How many mole? 1 mole. 1 mole of anhydrous salt to convert it into hydrated salt by specified amount of water. Amount of water should be specified. Just with the two example, you can say that what is the meaning of specified amount of water. Copper sulfate can take up 5 moles of water, whereas a barium chloride can take 2 moles of water. Okay, enthalpy of hydration. Then now, next we'll move to what, children? Let us move to the enthalpy of neutralization. Okay, enthalpy of formation we have completed, combustion, solution, and hydration. Let us move to what? Enthalpy of neutralization. Enthalpy of neutralization. Enthalpy of neutralization. Okay. Enthalpy of neutralization. Enthalpy of neutralization, it is abbreviated as delta HN. We know the meaning of neutralization, that acid is added to base to form salt and water. Since our childhood we said that what is neutralization? By mixing acid and base to get a salt and water is called as neutralization. But you cannot define as what you have defined with respect to the 7th standard or 8th standard. Now, neutralization we should define in terms of their equivalent weight. Have you remembered, children? The first topic we have completed, stoichiometry. At the time of stoichiometry, we said related with water titration, related with neutralization. What we said, that the amount of heat release, because neutralization is always exothermic. Neutralization is always exothermic. Delta H will be negative. Neutralization is always exothermic. The amount of heat release when 1 gram equivalent weight of the acid neutralizes with 1 gram equivalent weight of base. Okay, we can say, let me repeat the sentence once again. The neutralization is nothing but acid plus base gives salt and water. Acid plus base gives salt and water. It is commonly called as neutralization. But how to define? That should be defined with respect to their equivalent weight. Equivalent weight, because always you need to remember that whenever we are going to take HCl and NaOH, when we are taking HCl and NaOH, the basicity of HCl is 1, acidity of NaOH is 1. Both are 1 and 1. So it means that 1 gram equivalent, 1 mole of HCl can be neutralized with 1 mole of NaOH, because HCl basicity is 1, sodium hydroxide acidity is 1. Same thing you cannot expect in sulfuric acid, because sulfuric acid is a dibasic acid. Sulfuric acid is a dibasic acid whose basicity is 2. Whose basicity is 2. For example, if you are going to take sulfuric acid and NaOH, sulfuric acid and NaOH. Sulfuric acid is a dibasic acid. Sodium hydroxide is a monoacidic base. That means that if the question arises with the different acidity and the basicity, because we know very well that whenever we are defining the equivalent weight of acid, equivalent weight of the acid is nothing but what, children? Equivalent weight of acid is nothing but molecular weight of acid divided by basicity. Molecular weight of acid divided by basicity. Molecular weight of acid divided by basicity. Same way, if I am going to take equivalent weight of base, equivalent weight of base will be equal to molecular weight of base divided by acidity. Divided by what? Acidity. So it means that whenever we are going to define with respect to equivalent weight, the neutralization will be defined in terms of equivalent weight. Therefore, the enthalpy of neutralization. That's why what we can say, enthalpy of neutralization. Let me repeat the sentence. Enthalpy of neutralization can be defined as the amount of heat liberated. Accompanied also you can say, no problem at all. Accompanied also you can say, but you need to remember that enthalpy of neutralization will be always exothermic. Amount of heat liberated. Amount of heat liberated. When 1 gram equivalent weight of acid neutralizes completely with 1 gram equivalent weight of base. 1 gram. Okay. Equivalent. 1 gram equivalent weight of acid with 1 gram equivalent weight of base. 1 gram equivalent weight of acid is going to be neutralizes with 1 gram equivalent weight of base, and the heat liberated at that point is called as enthalpy of neutralization. So here enthalpy of neutralization is nothing but amount of heat accompanied, and always amount of heat will be liberated during neutralization when 1 gram equivalent weight of the acid is neutralizes with 1 gram equivalent weight of base. Okay, 1 gram equivalent weight of base. Children, have you remember that even in the equilibrium topic we said acid may be strong, acid may be weak, and acidic strength of, that is the strong and the weak strength of acid, can be decided on the basis of alpha value. Alpha is nothing but what? Degree of dissociation. All these points already we have read in the previous topic, equilibrium, that is ionic equilibrium. Now, if we'll observe that if acid and base both are strong, if acid and base both are strong, then enthalpy of neutralization will be constant. If acid and base both are weak, one may be weak, one may be strong, enthalpy value will not be constant. Why it is so, that we'll see one by one. One thing we need to remember, that enthalpy of neutralization, enthalpy of neutralization, enthalpy of neutralization of strong acid. Okay, strong acid with a strong base is always constant. Very important question. Very important question for competitive exam. Enthalpy of neutralization of any strong acid with any strong base is always constant. Why it is so? First we will write the example, after that we will see. Here, if I am going to take hydrochloric acid in aqueous medium with sodium hydroxide in aqueous medium, okay, they are going to produce water, sodium chloride solution. They are going to produce sodium chloride and water. Sodium chloride and water. Remember one thing, whenever we are going to take with respect to acid or the base, whenever we are going to take with respect to strong, because hydrochloric acid we can take, or we can take sulfuric acid, or we can take nitric acid. Any strong acid can be taken. Even we can take HI also, because HI is the strong acid. Therefore, a delta H value will be always minus 57.3 kilojoule per mole. How much? Constant value will be how much? Minus 57.3 kilojoule per mole. So in a simple way, we can say that whenever the acid is strong acid with a strong base, the enthalpy of neutralization will be constant as minus 57.3 kilojoule. Because when the hydrochloric acid we are going to dissolve in water, they are going to produce what, children? H plus Cl minus, and sodium hydroxide will be producing water, Na plus OH minus. Then on the product side, we are going to get water, Na plus Cl minus and H2O. Therefore, common ion can be cancelled over here. Okay, if ions are common, what is left out? Tell me. H plus OH minus converted into water. If they are asking the question that how to define enthalpy of neutralization, enthalpy of neutralization can also be defined as the amount of heat liberated. The amount of heat liberated for the formation of water, from H plus and OH minus ion. And always you need to remember that whenever we are going to take the question, whenever we are going to choose the option amongst the four, then if they are asking the question that why the enthalpy of neutralization of strong acid with a strong base is constant, we can define either with respect to what, children? We can define with respect to neutralization, or we can define with respect to formation of water. And the formation of water enthalpy value will be equal to what, children? Minus 57.3 kilojoule. In some of the books, even they have taken it as water, minus 57.4, nothing to worry for that. Okay, that's why whenever you are going to take with respect to enthalpy of neutralization, we need to remember that the enthalpy of neutralization is nothing but amount of heat liberated when 1 gram equivalent weight of acid is neutralizes with 1 gram equivalent weight of base. And during that neutralization, actually there is a formation of water molecule. That's why enthalpy of neutralization in one more way can also be defined as the formation of 1 mole of water from H plus and OH minus ion. H plus and OH minus ion. One sentence what I said, strong acid with a strong base is always constant, because strong acid and the strong base will undergo complete ionization. Strong acid and the strong base will undergo what, children? They will undergo complete ionization. Strong acid and a strong base will undergo complete ionization. If they are asking the question, remember one thing, question can be written in different ways. Neutralization can be defined in terms of equivalent weight. Neutralization can be defined with respect to this. Even it can define that strong acid and a strong base will undergo complete neutralization. Strong acid and a strong base, when they undergo complete ionization, whole molecule are split up into ion. Whole molecules are split up into ion. That's why we can say that we are going to write with respect to the complete neutralization. Okay. So here, let me write once again. Instead of taking this one, if we are going to take any of the molecule like nitric acid, like we'll take another example, nitric acid, HNO3 with potassium hydroxide. Potassium hydroxide. In aqueous medium, nitric acid and the potassium hydroxide will get it as potassium nitrate KNO3 in aqueous medium and the water H2O liquid. Delta H value will be again same. We can write the delta H value as minus 57.3 kilojoule. minus 57.3 kilojoule. Whereas if I am going to take, instead of taking this, if we are going to take acetic acid, okay, acetic acid is a weak acid. As we know very well that acetic acid is a weak acid. It will undergo partial dissociation. Partial dissociation when treated with the sodium hydroxide. Okay, when it is treated with the sodium hydroxide, because acetic acid is a weak acid, sodium hydroxide is a strong base. Strong base, weak acid with a strong base. Remember one thing, weak acid will undergo incomplete ionization. So it means that to make it to complete ionization, amount of heat energy must be supplied over there. Are you getting my sentence? Amount of heat energy must be supplied over there, because they will not undergo complete ionization, but this will undergo complete ionization. But this will undergo complete ionization. This will not undergo complete ionization. This will undergo complete ionization. Therefore, we can write the product as sodium acetate, CH3COONA, in aqueous medium along with water. And always you need to remember that whenever we are going to take a weak acid or a strong base, or you are going to take any of the, what we can say, any of the strong acid with a weak base, strong acid with a weak base, or weak acid with a weak base, weak acid with a weak base, all these are having delta H value less than minus 57.3 kilojoule. Okay, very important point for the competitive exam. We can say that enthalpy of neutralization of strong acid with a strong base is minus 57.3 kilojoule. If one is a strong, one is weak, maybe acid may be weak, base may be strong, or acid may be strong, base may be weak, both may be weak, delta H value will be less than minus 57.3 kilojoule. This point we need to remember to understand enthalpy of neutralization. Enthalpy of neutralization. That's why whenever they are asking the question related with one strong acid, one strong base, or maybe one weak acid and a weak base. Strong acid and a strong base will be constant. Weak acid we need to subtract over there. Okay, that's why whatever, if for example amount of heat will be X, we can write it as minus 57.3 kilojoule plus X amount of heat energy which is supplied to dissociate completely weak acid or a weak base. Because all these things we are going to define with respect to, because when we'll go for the numerical section, children, we'll solve one of the two questions based upon this one. That time with respect to the X value we can remember. But this concept I need not to repeat once again in the tomorrow's class. That while solving the numerical, you need to remember that if we are going to take strong acid and a strong base, directly I'll take the value as minus 57.3 kilojoule per mole. Because already we have read just now that what a strong acid and a strong base will undergo complete ionization, enthalpy value will be constant. Enthalpy value will be what? Constant. But when one is weak, the enthalpy value will become less than minus 57.3 kilojoule per mole. It will be what, children? It will be less than minus 57.3 kilojoule per mole. Okay, let us move to the next one, that is enthalpy of phase change. Okay, enthalpy of phase change. What we said, enthalpy of formation, enthalpy of combustion, enthalpy of solution, enthalpy of neutralization, enthalpy of water, hydration. 5 we have completed. The sixth one is enthalpy of phase transition. Enthalpy of phase transition. Okay, let us come to sixth one. All type of enthalpy I'll complete one side. After that, when I'll go for the laws and the numerical, at a time we'll do all the water numerical section. Enthalpy of phase change. Phase change. phase change is nothing but what? Solid to liquid, liquid to vapor, or the solid to directly to vapor. Even we can consider one allotropic form to another allotropic form. Phase change, it indicates that there is a physical state, or we can say that one of the physical state, physical form are converted into another physical state. Solid may be converted into liquid, liquid may be converted into vapor, solid may be converted into vapor. One allotrope can be converted into another allotrope, but conditions will be different. In another way, enthalpy of phase change can be defined as the amount of heat accompanied during phase change. What we can write? Amount of heat accompanied. Amount of heat accompanied for change of physical state. For change of physical state. Physical state. Okay. Physical state is nothing but what? From liquid to solid, from solid to liquid, or we can say from liquid to vapor, or we can take from solid to vapor. Let us see one by one. Okay. Let us see the first one. Enthalpy of fusion. Let us see first one. Enthalpy of what, children? Enthalpy of fusion. Okay. Enthalpy of fusion. Enthalpy of fusion. All these symbolical representation just for our reference. Okay. Enthalpy of fusion is nothing but amount of heat accompanied. Our usual sentence will be heat accompanied. Amount of heat accompanied when 1 mole of a substance in solid state converted into its liquid state. At what temperature? Melting point. 1 mole of a substance, amount of heat accompanied. Amount of heat accompanied when 1 mole of a substance, 1 mole of a substance enthalpy of phase transition. Let me write once again the heading. Enthalpy of phase transition. Okay, in that what I said, enthalpy of fusion. Write once again, enthalpy of fusion. What I said, enthalpy of fusion can be defined as the amount of heat accompanied when 1 mole of a substance in solid state, 1 mole of a substance in solid state is converted into its liquid state. Converted into its liquid state at its melting point. What we can say? At its melting point. Amount of heat accompanied. We can say that enthalpy of fusion can be defined as amount of heat accompanied during the conversion of 1 mole of a substance in solid state converted into its liquid state. Delta H value can be taken it as plus 6.5 kilojoule per mole. Very simple to remember. Enthalpy of fusion. At its what temperature? At its melting point. One physical state are changing into another physical state. Solid to liquid is called as enthalpy of fusion. Then liquid to vapor is called as enthalpy of vaporization. Okay. We'll write here. Enthalpy of vaporization. Vaporization. Delta H of vaporization. How to define, children? Enthalpy of vaporization can be defined as the amount of heat accompanied when 1 mole of a substance, amount of heat accompanied when 1 mole of a substance in liquid state, 1 mole of a substance in liquid state is converted into its gaseous state. At what temperature? At its boiling point. At what temperature? At its boiling point. At its boiling point. We are going to take it as with respect to what, children? Let us take the example like water in the liquid state converted to steam. Converted to steam. Okay. Delta H vaporization will be equal to what, children? Plus 40.5 kilojoule per mole. Plus 40.5 kilojoule per mole. Just to look at over here, amount of heat accompanied for the conversion of 1 mole of a substance in liquid state converted into its gaseous state at which temperature? At its boiling point. Okay, when we are converting solid to liquid, it is enthalpy of fusion. Liquid to vapor, it is called as enthalpy of vaporization. Now let us see enthalpy of sublimation. Let us see enthalpy of sublimation. Enthalpy of sublimation. Name itself indicates that sublimation. Solid is directly converted into gas without converting into liquid state below its melting point is called as sublimation. Amount of heat accompanied. We can say that enthalpy of sublimation can be defined as amount of heat accompanied to convert 1 mole of a solid into its gaseous state without converting into liquid state. For example, I2 solid converted to I2 gas. Okay, delta H value will be plus 62.4 kilojoule per mole. Temperature must be below its melting point. Temperature must be what? Below its melting point. All these type what I have completed till now, children, very simple what I feel. Because with the name itself, we are understanding. Vaporization, liquid to gas, sublimation, solid to gas. By knowing this sentence, you can elaborate the sentence in your own way. But the thing is that solid to liquid at melting point, liquid to vapor at boiling point, solid to gas below its melting point. This point we need to be remembered. Okay, and the last one is enthalpy of what? Transition. Enthalpy of transition. Here only I'll write the, okay, enthalpy of transition. Enthalpy of transition is also called as allotropic transition also we can call. Transition in a simple way, even you can call it as allotropic transition. Allotropic transition. Allotropic transition also you can call. Therefore, whenever the term comes with respect to allotropic transition, like the carbon diamond and the carbon graphite, sulfur rhombic and sulfur monoclinic, phosphorus white and phosphorus red, it means that substance in one allotrope is converted into another allotrope. The heat accompanied during that is called as enthalpy of transition. Called as what? Enthalpy of transition. For example, carbon diamond converted to carbon graphite. Carbon carbon can exist in the allotropic form, like the crystalline form and the amorphous form, like the diamond form and the graphite form. Okay, when we are converting carbon diamond to carbon graphite, the delta H value will be equal to plus 1.9 kilojoule per mole. Plus 1.9 kilojoule per mole. Remember one thing, when we are converting one allotropic form to another allotropic form, we can write it at its transition temperature. At its transition temperature. Always remember here, carbon diamond and the carbon graphite. Have you remembered in the first class we said enthalpy value depends upon allotropic form. Carbon diamond undergoes combustion, will produce different amount of energy as compared to carbon graphite. Okay, by combining both the equation, we can get the transition from diamond to graphite. Therefore, diamond to graphite, even we can convert graphite to diamond also. Therefore, the amount of heat liberated or amount of heat absorbed, amount of heat accompanied for the conversion of one allotropic transition to another allotropic form. Below, okay, at what temperature? At the temperature as a transition temperature. Okay, in case of the enthalpy of the phase change, what we have discussed, enthalpy of phase change from one physical state to another physical state, like enthalpy of fusion, enthalpy of vaporization, enthalpy of sublimation, and enthalpy of transition. What we can say, enthalpy of transition. One point you need to remember, that always enthalpy of sublimation, always enthalpy of sublimation. Okay, enthalpy of sublimation will be equal to enthalpy of fusion and vaporization. Sum of enthalpy of fusion and enthalpy of vaporization. Okay, this formula you need to remember here, children. This formula you need to remember, that enthalpy of sublimation will be equal to enthalpy of fusion and enthalpy of vaporization. Enthalpy of what? Fusion and enthalpy of vaporization. Therefore, whenever we are going to deal it with what, children? Whenever we are going to deal with enthalpy of this one, conversion from one physical state to another physical state, or from one allotropic form to another allotropic form. Okay. Now, the next, this is about sixth one. Then we are having the seventh one, related with what? Enthalpy of atomization. Okay, next, right? Enthalpy of atomization. This is seventh one. Enthalpy of, are you understanding with the name? Yes. Why not? Atomization. Name itself indicates that molecules are split up into atoms. Name itself indicates that molecules are split up into atom. It is called as enthalpy of atomization. Here also we can define that amount of heat accompanied, or amount of heat, because when we are breaking a molecule into atom, we need to supply the energy. So we can say that amount of heat required. Amount of heat amount of heat required. We can say that amount of heat required to break 1 mole of bond. To break 1 mole of bond. Okay, we can say that amount of heat required to break 1 mole of a bond of a particular type. Okay, amount of heat required to break 1 mole of a bond of a particular type between two atoms in the gaseous state. Between two atoms in the gaseous state. Sentence is most important, children. Amount of heat required to break 1 mole of a bond of a particular type between two atoms in the gaseous state. Okay, in the gaseous state of substance. Gaseous state of substance. For example, H2 molecule. H2 molecule are split up into two hydrogen atom. H2 molecule in the gaseous state converted to two hydrogen atom. Okay, the delta H value will be plus 435 kilojoule per mole. Delta H will be plus 435 kilojoule per mole. Plus 435 kilojoule per mole. So what we can say, when we are dealing with 1 mole of hydrogen gas molecule are split up because hydrogen and hydrogen, this bond has to break. Are you getting the sentence? Enthalpy of atomization is nothing but what? Molecule are split up into atoms. Molecule are split up into atom. Even we can call it as dissociation enthalpy. Dissociation enthalpy, that we'll see later. So here we can say that hydrogen molecule are split up into two hydrogen atom. And another point, if I am going to take methane molecule, CH4. If I am going to take CH4 gaseous molecule, okay, if I am going to take the methane molecule are split up into carbon in the gaseous state, 4 hydrogen atom in the gaseous state, because methane contain 1 carbon with 4 hydrogen. Methane has 1 carbon with 4 hydrogen. They are split up into carbon and 4 hydrogen atom. And the delta H value will be plus 1665 kilojoule per mole. 6665 kilojoule per mole. That means that amount of energy needed to break a molecule into atom. Simple way. To break a molecule into atom, and the molecule must be in the what, children? Gaseous state. Molecule must be in the gaseous state. But this we cannot take with respect to what, children? When we are going to take bond enthalpy. Have you remembered that bond enthalpy, already bond parameter we have read in chemical bonding topic. That time we have taken it as a average type. For example, if I am going to take the bond enthalpy, bond enthalpy, if I'll take here, bond enthalpy. Bond enthalpy, how we have taken, have you remembered, children? Or bond enthalpy we have correlated with bond length. Even we have correlated with water. Even we have correlated with bond angle. So it means that number of bond also plays important role over here. That's why whenever we are dealing with water, bond enthalpy, always we need to take the average. Always we need to take average. Okay, that's why bond enthalpy, when we are taking bond enthalpy, can be defined it as it is the average of bond dissociation energy. It is the average of bond dissociation energy. It is the average of bond dissociation energy of the bond of the same type, of the bond of the same type in gaseous substance. In gaseous substance. Gaseous substance. Okay. For example, if we are going to take for a polyatomic molecule like water, water has two OH bond. Correct? When the water is split up, because water consists of water, two OH bond, O and H bond. Two OH bond. Two OH bond are present in water molecule. Therefore, bond energy can be taken it as water. It will be the average of both. Average of both. For example, if we are going to take, let us elaborate this example only, children. If I am going to take water, H2O, okay, H and H. When it is going to be split up, we'll get it as H plus and OH. Okay, we are going to get water. There is a formation of the two OH bond over here. We'll get it as H plus and OH bond, and the delta H value will be plus 497. Plus 497 kilojoule per mole. What we can say? Plus 497 kilojoule per mole. Same way when we are going to take OH split up into O plus and H. What we can say? OH are split up into O plus H. The delta H value will be plus 428. Delta H value will be what? Plus 428.48 kilojoule per mole. Okay, 428.4 kilojoule per mole. Therefore, bond energy of OH bond can be taken it as average of both 497 plus 428 428.4 divided by 2. Okay, let us take here 497 and this will be 428.4. We will add both the 4.77, 15, 16, carry 1. Okay, 7, 7, 14, 1 minute, 15, carry 1, 10 plus 2, 12, carry 1, 8 plus 1, 9, 925.4. 4 divided by 2. It will be equal to what? 2 4 is 8, 2 6 is 12, 2 2 is 2 7 is kilojoule per mole approximately. That means that when we are taking the average, when we are taking the bond dissociation energy, we need to take it as their average. Okay, this is all about all the type of enthalpies of reaction. Only one is left out, lattice enthalpy, and the two laws of thermochemistry. Tomorrow will complete. After that, we can solve. Only two numericals are there. Along with that, if this one, two more numericals we will discuss, children. Just to go through it, whatever we have covered today. Today we have covered all the type of enthalpies of reaction. Just to read the sentence with one example, try to understand. If any doubt, anything are there, just you can post a doubt to me. Okay, let us conclude now. We'll continue tomorrow. Okay, thank you one and all.